All right, let us begin. So we start with an announcement again, or like a quick note, a little thing that seemed to have confused some people, so I just wanted to mention it. Okay, so the data set and so there's this data set thing, and in the data set we label like the feature label pairs with this like x1, y1, xn vector yn. Okay, and here there can be some confusion in what a little bit of this notation means. So here this subscript, when it's like a subscripted for the vector, this means it's like the first vector, the first feature vector. This is the nth feature vector, right? This set calligraphic x like contains d-dimensional vectors. That's what each one of these things are in. Right, so in particular, what that means, I guess, is like this guy here is an element of this set, right? It's a vector. Then if we want to write it with its actually explicitly write the indices of the vector, there's d indices, right? It's a d-dimensional vector. We would write it like this. And here we use a second subscript to denote that this is like the first index, the first dimension. This is like the second dimension, and there's d dimensions, right? So that's for the x1 vector. For the xn vector, we use the same thing. Like this is the first index of it. This is the dth index or dth dimension. Okay. And then there can be some confusion when we talk about like some general vector, some arbitrary feature vector x, which we'll use for the predictor. So in the predictor, we won't use any subscript. We'll just say like, oh, we have some arbitrary feature vector x. How does it do on that? There, we also sometimes will want to explicitly write that it's a vector, right? And there we'll use this subscript 1, 2, up to d as well. But notice how there's only one subscript. There's not like these two things, because there was no original subscript to begin with. And so the thing to point out is that here, these things are like the indices of the vector x. And what they don't have is they don't have a hat above them here. They're not vectors. They're just numbers. And so the important thing is that like this x1 is not the x1 feature vector from the data set. Similarly, x2 is not the x2 feature vector from the data set. These are just the indices of this arbitrary feature vector that we might be interested in what the predictor will do. So this is a confusion that can come up. And I kept with this notation because later on we'll use matrices, and this is going to be the standard way to index things in matrices and whatnot. Sometimes people will put these in the superscript to make it like obvious what's indexing things. So yeah, just a note. Cool. Okay, and from that, yeah, we start the lecture. So today's lecture should be kind of fun because we're actually going to define the learner. So we're actually going to talk about how do we learn from the data set and how do we produce a predictor. So that should be fun. Okay. Just to recap from last class, like what happened is basically in last class we defined what does learning well mean. And roughly speaking, let's just get to the objective here. We had like two parts to the objective. So this is the almost formal one, which probably is easier to look at first, which is we said we just want to define this learner, right? This thing that takes in a data set outputs a predictor, such that this predictor that it outputs, which we call f hat, is going to be good at predicting labels. Like from unseen features, it can predict labels well. And how did we model this? Well, we model this with something called an expected loss. And just like in words, this thing measures so first of all, what does the loss measure? It measures how close is our predictor to predicting the correct label for some feature input. And then the expected loss is just the expected value of this loss, right? So it's like an expectation over all features and labels you might see, how small is this loss? You want it to be small. If it's small, it means you're predicting things pretty like almost correctly. And formally, this expected loss was written like this, right? What it did was first there was something called the loss function. This loss function took in our predictor and compared it to a label. When these things are close, this thing is small. That's what the intuition is. When the predictor predicts the label correctly, this is small. And since we have no idea what the feature we're going to receive is, right? We want to do good on average over these features and labels we're going to get in the future. We take the expectation. Great. So that was the story. And then there was just this slight informality, which was that there's we learned this predictor, but the thing is we are going to learn it from data somehow. And the thing is the data might be we don't know what the data is that we're going to get. We're going to get some data. And depending on the data, we're probably going to learn a different predictor, right? If this thing is doing any learning from the data, it means that if the data changes, you're probably going to learn something different. Meaning, yeah. So what that meant is that like this is kind of imprecise because like the f hat you output depends on the data, which then means like, okay, for which data sets do you want to do well on? And so the answer and like the solution to this was to make a new objective, which was like this. You want to do well on like in expectation over data sets, and well meant here that you do well on the expected loss, right? The expected loss that you output for each data set. So there's two expectations. This is like a complicated looking object because when you expand this, there's another expectation inside and so on. So what we said is, okay, we're going to kind of like not talk about this exactly in this way for now, and we're going to like do a simpler thing, which is we're going to think about like let's forget about the data set being random for the most part, and we're going to just we're going to have like this calligraphic D data set. Like we have some fixed data set. Let's just talk about like if we had this data set, how would we use it? How would we use it? And by we, I mean, how would this learner A use it, right? It's taking it as input to produce a good predictor. So that was where we ended. Like, how are we going to do this? And so we start with answering this question in a sort of naive way, and then we get to the algorithmic paradigm, or like the learning paradigm that we're going to basically use for the whole class and is used in all of machine learning. Okay, and so we write something like our approach. Okay, and so we start with like what someone mentioned in the last class, which is like the most naive thing that you'd want to do, and that is like, okay, so let's suppose that f star, or let f star be the f that minimizes, right? Minimizes what? Minimizes the thing we actually care about, which is the expected loss. Right? So like f star is the one that minimizes this thing. Our goal is to minimize it. So we should, so what? So this learner should just like f star, or sorry, this f hat should just equal f star, right? And so this is what we would want. But the problem is, so what's the problem? Well, the problem is we don't know what this expected loss is for any f. And like, why don't we know it? The reason we don't know it, since we don't know the distribution P of x, y. And let me just scroll like, okay, so if we could compute this expected loss for each f, then what would we do? We would just like pick, like try all the f's and then pick the one that has the smallest loss, right? Then we would just output that. But the problem is we don't have access to this function. And what I mean is we don't have access, is like, let's look at the definition of this thing. Right, where was it? So it was like this expected loss thing, right? And the expected loss was under what? It was under this distribution. So to compute it, I kind of wrote it out explicitly. It's like, to compute it, we would have to use like this PMF, or sorry, here, the PDF, and do these integrals. But no one's giving us the PDFs. Like, at least not in our problem setting. Okay, maybe you can define some other weird setting where someone gives this to you, then you just compute this thing and you're done. But in our problem setting, we don't have access to this, right? But what we do have access is from some data that came from this distribution. And so here's the whole machine learning part. Like the data part is coming from this distribution, and that's like our experience that I was talking about in the first lecture. And we're going to try to somehow use this data, right, to learn what this is, and then basically we're going to pick a good predictor based on that. Okay. So I kind of like foreshadowed how we're going to address this problem. So let me just copy and paste this objective so it's here as well. Okay, so we had this thing. So this was like this loss thing. Okay. And so now I actually write how so this is how we're going to define our learner. So let's call this thing defining the learner. So here we go. We're finally defining what is this learning algorithm going to do. And this might be a little underwhelming because it's going to be very simple sounding. Okay. So first of all, I'm going to give it an, okay, I'm not going to give it the name first. I'm going to just describe it. So there are going to be two steps. Estimation. So the first step is this estimation step. And guess what we're estimating? Okay, so we're going to use the data set to estimate this expected loss, okay, for all functions, okay? And here I'm going to just say something and we'll talk about in a second. For all functions in some set called f, which is going to be the set of all functions we consider, okay? And this set is usually going to be, well, it's always going to be a subset of all possible functions. But most of the time, we're going to pick this to be like a strict subset. And the reason to pick a strict subset is it's going to be easier to pick, to search through it, and we'll talk about this in a second too. Okay, but like this should make a lot of intuitive sense, right? We don't know this thing. We have data. So what do we do with the data? We just estimate this thing. Okay, if we can estimate this thing, well, if the estimate is good, then what do? We do exactly what we wanted to do at the beginning here, which is just pick the best f, like the one that minimizes this thing. But now it's going to minimize this estimate. So the second step is going to be, okay, I'm going to call the estimate so this hat thing we'll see in like just in a couple minutes, this hat thing usually indicates that something is an estimate. Whenever we put hats above things, it means something's estimating something. So this is our estimate of the expected loss. And so the second step is called the optimization step. And this is just like, I guess, a fancy word for saying we pick the best f based on this thing. So what does this step do? It says pick f hat, right? That's what our algorithm is going to do. It's outputting this f hat. So pick f hat, right, to be the f that, and I'll make it explicit again, f, which is a element of this set of functions we're looking over, that minimizes this L hat thing. Okay. So here's our function, our learning function. And believe it or not, this is actually at the heart of all of machine learning algorithms. And basically, this is like, there's details on how we're going to do these steps, but these details exactly are the things that are followed by like the algorithms that, for instance, like that ChatGPT and stuff implemented. And like, yeah, okay, I'm going to say a couple more things. So maybe just like high level, yeah, you're going to use this data to estimate this like loss thing, and then there's going to be some optimization procedure, and it's not going to be as naive as one by one look through everything in this function class and just try and test these values and pick the best. There's like infinitely many functions, so we're going to have to be more clever, and this like more clever thing is going to be this optimization theory stuff, which we'll talk about. But at the end, there's going to be like, you're going to need to use the derivatives or gradients, and you might have heard this term before in machine learning called gradient descent is going to like help us here. But yeah, there's just like 2 steps you really need to do. Okay. And I wanted to mention one more thing, which is that in like, sometimes this, like, okay, this is like the more theoretical thing, but like sometimes people will call this function empirical risk minimization. Okay. And for short, you might hear something like ERM. And what is this risk business? Well, it turns out that people will often call this thing, like this thing's called the risk as well. Expected loss, risk, these are, I don't know, they use the same word for it. Okay, so like, what are we doing? We're like empirically, which means we're using data. This is the empirical part. We're using data empirically. We're minimizing the risk. Okay, so we're minimizing the empirical risk. Basically what's happening. So yeah, this is going to be like the algorithm we study for the rest of the class, essentially, and how to implement this. Okay, and I give like some like very high level examples of what this algorithm ends up doing like with data or something like that. So we do the house example again. And here, suppose we had like this number of rooms. And here we had the price. Well, then if we saw like a bunch of data, I don't know, something like this, right? Then what we would do, and let me maybe write this in words, is the first thing we would do is we have to first like pick what functions are we going to consider. Like what is this set of functions we're going to search over for which our predictor is going to come from. And it's going to turn out that like this thing is called the, okay, we'll give it a name. This thing is also going to be called the function class. It's going to be the class of functions we search over. And we want to pick the best one from that. So we should pick a function class. So let's let be all linear functions. So this would be like all the lines in 2D, right? And then what does ERM do? Well, ERM, like roughly speaking, ERM picks the line that best fits the data. Okay, so this is like what it's roughly speaking going to do, and that would mean something like, I want to try all the different lines, which means like, okay, it's going to like maybe consider like this line. It's probably not a great line. Why? Because like its loss, which you would measure as the distance, right? It's estimating a value here, and it's going to measure it relative to like each one of these data points, something like this. So this is going to be like farther away than something like, and all this right now so far is just like high level intuition. Don't worry if like the exact things don't make sense and stuff. I'm just trying to give you an idea of like what ERM would do. So it'd probably pick something like this. So this would probably be f hat. Okay, and this like purple line is just an example of something you might consider in this function class, but wouldn't pick because its expected loss, or sorry, its estimated loss is going to be quite large. Okay, so that's going to be this like fitting the data with the best line. That's what ERM is going to do. And like you could, like another example, I'm not going to write it, is like all that changes when you work in like the actual world of machine learning stuff is this thing, this thing instead of being lines is just neural networks. Okay. And so like for ChatGPT stuff, like ChatGPT 3.5, for instance, it searched over all neural networks of like a special type, but like they all had 70 billion parameter neural networks. Okay, they had exactly as many parameters, and that's all they did. So they had to search over all these type of neural networks. That became like a complicated search, and so the optimization was hard, and they needed all this computation stuff. But the story was essentially the same. They had some loss, which was like how close they were to predicting the next word. They didn't know what the true loss was from like all the data. They didn't know what the true loss was. So what they did is they used data to estimate this. And then they searched over all the neural networks and picked the best one. And then they output it. And that was ChatGPT, like roughly speaking. Okay, so what are we going to do now? I give you some examples. So what we're going to do now is we're going to go into this part. Like we're going to talk about how we do this. And then we're going to spend a lot more time talking about how we do this. And then we're going to like talk about whether we did it well or not at some point in a few more weeks. But the goal is to get this covered today and the very beginning of this in a very simple way covered on Tuesday, and then you'll have your midterm on all that content up to now. Okay. And someone said, I thought we weren't testing all of F in LF since they're infinite. Isn't that what the dots represent? No. But so we are going to test all of these F in F. And that's the difficulty of the optimization. How do we test them all? We'll use derivatives to help us. And these dots, they don't represent functions. They represent data. And we're trying to pick the function that's going to best fit the data. It's going to have the best estimated loss. And I haven't explained what this estimated loss is at all. I told you it's going to be based on the data. You might have some intuition how we're going to use data to estimate it. Haven't told you, that's what we're going to cover in a second. But like, roughly speaking, you can see like, okay, I can maybe measure the distance here, and then I would square it because we're going to care about like the squared loss and stuff. Okay, well, this will be all more precise in a second. Is there any questions before we get into estimation? Yeah. So this is going to be this is the output of our learner. And like if the learner is doing well, which it will for the simple cases we have, it's going to output the f in this function class, which is lines in this case, that minimizes this expected loss. Oh, sorry, the estimate of the expected loss, which I don't like, we're going to talk about it. Like, is this thing close to the true loss? Like, we really care about the true loss. Is this thing a good estimate of it? If it's like a bad estimate, then like maybe we're like, sure, we minimized over this estimate of it, but like if it's the wrong thing, then like that's not good. So there's going to be two steps. It's like, make sure this thing is close to this. If that is true, then it's fine to just work with this thing. Just pick the best one based on it. And there'll be some, like this will be an important detail coming like in 3-4 weeks about how good that estimate is. For now, we're just going to, when I talk about it in a second, we're just going to, you'll see. We'll be a little bit naive with our hopes and dreams. So let's start on the optimization stuff. So the L can be any function. Like the loss can be anything you choose. And depending on the loss you pick, the F you pick is also going to probably be different. But like, and the function class is also based on your choice. So, but like the thing like the F you actually output, the predictor, is something in your function class that you choose at the end of the day. Okay. So let's start with optimization. Optimization. Okay. And so here we're gonna unfortunately have to take maybe like 20 minutes to go back to the basics and explain some math stuff again. Oh wait, why are we doing optimization and not estimation? This is a mistake. Okay, let's forget about this guy. We talk about estimation first. Sorry. Okay, we're doing estimation. We need to estimate the expected loss. Okay, yeah, so we're gonna have to go with the basics of estimation first. We're gonna forget about learners and stuff for just maybe like 20 minutes, and then we'll come back. Okay. Roughly speaking, what is this like optimization business or estimation business? It's gonna be something like gonna be finding. Oh, let me just make sure I open the right notes here as well. It's going to be roughly saying like you're going to be using data, okay, to do what? To approximate some fixed object. You can already see how this relates to our thing. Like the fixed object is going to be this expected loss. That's just like some number. We're going to want to approximate that. And it's like common examples of things or these objects are like things like estimating the mean or variance of a random variable. These are the things we're really going to care about, like especially the mean. And the mean, right, is the expected value. And we had that loss function, which took in random features, random labels. That was the random variables. So the mean part's going to be very important. So we're gonna focus on the mean thing. And we're going to start with the example of doing this with coins. Okay. So let us start the story here. So let's suppose that we have an unfair coin. Okay. And I say unfair just to like make it interesting that we would actually like, we don't know what the unfairness part is. So let me make this a bit more formal. So that means we have like a random variable which comes from the set 0, 1. Okay, 0 is going to represent tails. This is going to be tails. 1 is going to be heads. We've seen this before. And this is, okay, I'm not going to write, but this is representing the coin flip, right? The other thing I'm going to say is that x is distributed, so it comes from this distribution for x, and that distribution is a Bernoulli distribution because it's a coin flip. So I would write something like this. And I have to write the parameter, which is alpha. So this tells me the unfairness level of the coin. If alpha is 0.5, that means the probability I get heads is 0.5. If alpha is 0.8, the probability I get heads is 0.8. Okay, that's just reminding you what that represents. And in particular, we'll need it in a second, so I'll write it. So probability, this is the PMF. The PMF of 1 is equal to alpha, while the PMF of 0 is equal to 1 minus alpha. Okay, great. So there's something else we talked about, which is the expected value of flipping a coin, which is the expected value of x, right? And I think we did this calculation before, but we'll just do it again. The way you do this is you do it through the PMF, and what you do is you consider all the little x in the outcome space, which is 0, 1. Then you multiply the little x, the values it takes on, by its corresponding PMF value. Okay, so explicitly, that means you would get 0 times the PMF value of 1 minus alpha, right, plus 1 times alpha, which gives us, as we would expect, the expected value of the coin flip is going to be alpha, which is exactly its level of unfairness. Okay, great. But do you really ever know this expected value? You have this coin. Maybe, okay, someone might tell you the expected value, but let's suppose, okay. So here's the interesting thing is suppose you don't know this expected value. And once again, you can imagine how this is related to our machine learning thing. We don't know what the expected loss is. Suppose we don't know this thing. And so here we ask the simple question for the coin case, which is how do we estimate alpha? Okay. And at this point, you might be thinking okay, well, how much is there to really say here? You're probably your first guess is okay, I just do I flip the coin a bunch of times, I take its average and then use that. And honestly, that's basically what's going to happen. That's exactly what we're going to do. And we're going to spend 40 minutes doing that, explaining some details and math and stuff. But that's the whole intuition. You're just going to flip the coin a bunch of times, right? And then you're just going to take the average of those values. But we're going to talk about some properties of this thing and stuff. And then we're going to do the same thing for the expected loss. Okay. So I kind of have told you the answer to this whole story, but this is how you're going to mathematically write all this information and talk about how good this we call it the sample mean is and stuff like this. So let's do the story. So the answer is you'd probably flip the coin multiple times. And take the average. Okay. And the way we're going to talk about this is we're going to define a new random variable called z. And this z is going to be a multivariate random variable of n coin flips. So it's going to have x1 all the way up to xn. And each one of these is representing the value, or the random value, of coin flip number 1, 2, 3, up to n. So we've done n coin flips. Each of them are random. They're going to come up either 0 and 1. And so this has each one of these has the outcome space of 0 and 1. And since we have n of them, it's the Cartesian product n times. And so this represents, so we're going to represent our n coin flipped. Okay. You can hopefully see how this is related to our data set of n feature label pairs. Okay. We're going to repeat all this in a second for the data set stuff. Now, the important thing is that each one of these comes from the same distribution. which makes sense, right? We're flipping the same coin over and over again. So what is that distribution? It's the exact same one we've just seen. So it's Bernoulli alpha, right? And the important thing is that you're not choosing like coins based on the other flips and stuff. So the way we express this is we also say that they're independent. Okay. So hopefully you're also seeing how this is very similar to what we talked about with our data set. We had these feature label pairs, which I before just like gave them general names of Zi, Z1, whatever, and I said they're like independent and identically distributed. This should be a very helpful example to think of that. Okay. Now I'm going to define a new object, which is going to be exactly this average of the coin flips I got. So I'm going to write that as like a function of random variables, right? It's the function of the random variables x1 to xn. And right, we said a function of random variable is always going to be a random variable. And that random variable is exactly the average. So we'll write it as x1 plus all the way up to xn. So we add them all up. And then we divide by how many flips we had, which was n. This is like exactly what we've seen. Should be also hopefully quite simple. And another way to write this using the summation notation we've used in the class, which will be extremely helpful to save on space throughout this course, is you would write you take out the 1 over n to the front, so that's you divide by 1 over n, and you sum from 1 to n over each one of these coin flips values. Okay, so this is equivalent. So hopefully at this point everything still looks very simple, and you might be thinking like, okay, do we really need to do all this work? And okay, so this thing has a name. This is the name we're going to use for it throughout the course as well. This is called the sample mean. Okay, we're trying to estimate the mean, that mean expected value, the same thing, based on samples. Here it's n samples. Let me just write one more thing, and I'll take the question. So it turns out this thing, as I said before, sometimes we like renaming functions of random variables to other random variable, like just like symbols. And this has two common symbols you will use. Okay, one of them is you would use x bar, or you'll see and stuff. So I wanna put this out there, and maybe it'll end up being used in places. So there's x bar. This represents like the sample mean. And notice how this hides a bunch of information about this being a function. And in probability of courses, you'll just see x bar equals this thing, and then you're like, okay, but like this is like the explicit thing. This thing really is a function of random variables, which itself is still a random variable. So this will be important in a second. And the other way to write this is that, remember, what is this thing trying to estimate? It's trying to estimate alpha, right? So instead of writing alpha here, you write alpha hat to represent it's an estimate of alpha. And sometimes we'll also put like n to signify that it's based on n samples. Okay, this hat thing is a very important thing. Like, does anything remember? Hats almost always are going to represent estimates of some quantity based on random variables. Okay, now I can answer the question if you still have it over there. No, so okay, in this case, so if you change the distribution, for instance, you would still use this. So the sample mean can be used to estimate the mean of any random variable. Okay. Here, the mean we talked about for the Bernoulli is alpha. So this thing is an estimate of alpha in this case. And I'm just going to write this, but then erase it briefly, which is like, if instead, say we had the normal distribution, and there we usually have mean mu and variance sigma squared, well then what we would say is that we would say this x bar thing is actually an estimate of mu hat. So this is like notation you're going to see. Like, this is like kind of general. It says this is just the sample mean. And the thing it's trying to estimate is mu, so you write the mu hat, and these are all going to be like you can use all this stuff. So yeah, so the sample mean can be used to estimate the mean or like expected value of any random variable, and different random variables have different expected values. So you'll also like use this notation to really like clarify which random variable and which expectation you're working with and stuff. Yeah. Okay. And like, just foreshadowing, remember, what was the expected value we had? We had like this thing, L of F. That was an expected value. What do we write? We write L hat. Okay, we're going to see that in a second. Okay, great. So we have this thing. And then it turns out we can do we can actually talk about some properties of this, because this thing is a random variable. All right, so here's like maybe a thing that's a little bit weird to do, is you can talk about the expected value of the sample mean, right? So this sample mean is trying to estimate the expected value of a coin flip X. But it itself is based on n random variables. So you can ask, what is like the expected value that the sample mean will be? Like how, like, is the expected value actually going to be the true mean? Maybe it's like close to the true mean and stuff like this. So we can write something as the following, which is, we can say, what is the expected value of alpha hat of n? And this makes sense. Alpha hat of n is a random variable. It's a sum of random variables divided by n. But nonetheless, we can do this. And we'll work this out right now. And this is a useful exercise to give you kind of like two intuitions and also get to comfortable with working with these expectations and their properties. So what do I do is first I just plug in the function like explicitly. And that would mean plugging in 1 over n times x1 plus up to xn. Okay. And now what we do is we make use of like some properties of expectations, which is, first of all, if you have a constant, this is a constant number, then you can take it out of the expectation. Okay. So we've done that. And if you have the sum of random variables, to see how these are summed up in an expectation, that's the same thing as the sum of their expectations. So what that means is I can write the expected value of the random variable x1 plus all the way up to the expected value of xn. Excellent. Okay. At this point, this turns out to be very simple because remember, each one of these has the same distribution, right? These come from the same distribution as this guy here, like as this x. So what that means is that their expected values are all the same. So what I can do is I can equivalently write that this is just equal to 1 over n, right? And then plug in the expected value of x for each one of these things. Okay. They all have the same expected value. That's all I'm saying. We know what it is. It's alpha. So this thing just becomes 1 over n times n alphas, right? Which is just alpha. Okay. It's a pretty straightforward calculation, but what it communicates to us is that the expected value of the sample mean is actually the true expected value of the thing we're trying to estimate. So this is a nice property. Okay. So we actually are like, in some sense, estimating the thing we want. And like, yeah, maybe the main takeaway is like, I'll write this here, which is what you end up getting is that the expected value of this thing is equal to the expected value of like x bar, which is also equal to the expected value of x, which is equal to alpha. Like all these things are equal. It's great. Okay. Now let's go over like an experiment trying to like understand what it means to take like why are we taking expected value of this like sum of random variables and stuff? Like what does it mean for it to be random? So high level, I'm going to draw some plots in a second, but the high level thing is, right, like if I were to, let's say like n was equal to 5, which is what I'll do here. If n is equal to 5, like any particular time I actually flip 5 coins, I'm going to get a specific 5 coin flips, right? And then if I take the sum of those and divide, who knows what I'm going to get? Maybe I'll get alpha. Maybe I'll get something less than alpha. Maybe I'll get something larger. And so what is this expectation doing? It's saying that like if I flip the same coin 5 times, and I do this infinitely many times, what is the average value I'm going to get of the average value of those 5 coin flips? And that says that that's still going to be alpha. So let me just draw one plot that will hopefully make this a lot more clear. And then we'll move on. Okay. So here is how what I'm going to draw is I'm going to draw like, let's say we do 4 different experiments. So that means we're going to flip the coin 5 times, 4 separate times. And we're going to look at like the specific outcomes we get. Okay, so we do 4 experiments. So I'll call this experiment number 1, which means I flipped the coin 5 times. Here's another time I flipped the coin 5 times. Here's another time. and here's another time. Okay. And then what I'm going to talk about is like, what value do we, okay, so I'm going to draw 0 here, and I'm going to draw 1. Okay, these are the possible outcomes of the coin flip. And now here is how I'm going to like denote the experiments. So I'm going to flip the coin 5 times, and I'm going to draw an X for each of the flips. So for the first experiment, let's imagine maybe on the first flip I got a 0, which means I got tails. And then, okay, let me make something clear as well, is that I'm going to choose n equal to 5 here. Okay. And so, yeah, so now I'm going to flip this coin like 5 times. And maybe in the first one I got a tails, and then after that I got 4 heads. So I'm going to write like, these are all technically right on top of the 1 point. So, okay, so this is like one experiment I get. Then what is this like sample mean thing? Well, the sample mean from this data would give me something like, I'm going to write it like this. The estimate from 5 data points is going to be 4/5. Right? And I'm going to draw this point right here. This is like the sample mean estimate, and I'm going to plot it as 4/5. Okay, so that's like based on the first experiment, I get a sample mean of 4/5. So I suppose you can see where the story maybe is going. Let's imagine I do another experiment. I get the first flip is like tails, then I get heads, then heads, then heads, and then I get tails again. Okay, so now I calculate the sample mean again. Notice how it's different for these 5 flips. Now it's going to be something like 3/5. So I'll write that alpha hat for this red experiment is equal to 3/5. Okay, and then yeah, that's over here. Okay, and then I do that 2 more times. Suppose for this one, I get all of them as heads. Well, then my sample mean estimate is like 1. And so then I write alpha, that is 1. And then I do it 1 more time, and maybe I get some like weird outlier event, right? And I get tails, and then I get tails, and then I get tails, and then maybe just 1 heads, and then I get tails again. Now I have a very different sample mean estimate, which is alpha hat, the orange one, and that's 1/5. Okay. So this is like, you can see that depending on the values that these random variables take on, right, which is these 5 things take on, in your actual experiment, the sample mean could be very different. And so what did we calculate here? What we calculated was the expected value, right, of this thing across all possible flips of 5 coins and their corresponding probabilities. And we said that like, okay, you're going to have all this like variation. One time you're going to get this like underestimate of alpha maybe. I didn't say what the true alpha is. Like maybe the true alpha, I don't know, maybe the true alpha is 0.8, let's say. All right, let me do it as a fraction. Maybe it's 4/5. But you're doing all these flips and so on, and then you're getting estimates. The story is that like if you take the average of infinitely many of these type of experiments and weigh them by their corresponding probabilities, which is what the expected value does, you actually get back this true alpha thing. Okay. That's what I wanted to communicate here. Yeah, that's good enough. Okay, cool. So let's talk about one more thing related to this experiment, which is that notice how like, as we said, like depending on your like the experiment you do, you might get different sample mean estimates. And so you might say that like, you know, the sample means have some variance between them, okay? And this actually makes sense, like in a very rigorous way. Like you can actually talk about the variance of your sample mean estimate. Okay, and this is also going to be important for like our high level intuition, which we can say, what is the variance of this sample mean random variable, okay? This is saying like how much does it vary between experiments? Okay, so we can calculate this as well, and it's also not very complicated using the properties of variances. And here we're finally going to see why. So we saw already why it was important that these were all coming from the same distribution, right? These were identically distributed. Each of the coin flips came from the same Bernoulli distribution. What we haven't used is independence yet. Okay, and this independence, for the first time, we'll kind of see like it being used as well, and this is where it's going to come in. Okay, so we write this thing explicitly as before, which is that the variance of 1/n of x1 up to xn. Okay, great. Now we use some properties about variances, which was in the probability section, and I'm just going to give them to you, which is that if there's a constant, unlike in the expected value, this thing doesn't just come out, it comes out, but it gets squared. Because if you remember, the variance was like this difference from the expected value squared. So there's this 1 over n squared thing. This will be like on a formula sheet and stuff. You can look it up, but like this is how you do it. And then comes a crucial step, which is that since these random variables are all independent, the variance of the sum of things is equal to the sum of the variances. Okay, and independence is critical for this. So I'm going to put that we are using independence here. That's not how you spell it, eh? Oh, there we go. And now we have the sum of the variances. So that will look like the variance of the first random variable x1 all the way up to the last guy. Excellent. So this is a really nice form because it turns out, okay, we didn't calculate it at the beginning, but I'm gonna give you some. Okay, let's do one thing. So first of all, recall that all these random variables are the same, right? They're identically distributed. So we're gonna reuse that, and we're gonna plug in that this is just the same thing as the variance of x, summed up n times. Okay. Finally, we need to know what is the variance of x. So it turns out you can also calculate this variance thing. I think I was planning to do it. Okay, maybe I wasn't. But okay, you can calculate it. I'm actually not even going to plug it in. It doesn't matter, because the point I actually wanted to make. Now I just remember. So you end up with 1 over n squared, right? And then you have n variances. So you have n and then times the variance here. So the point of the story is what we get back is that the variance of the sample mean estimate is not the variance of the original coin flip. Okay, so the original coin flip has some variance, meaning that like when you flip heads and tails, when you flip this coin over and over again, there's like some variation in if you get heads or tails. The sample mean estimator, like intuitively, right, if you increase n, if you get more flips of the coin, you would probably expect that when you run this kind of a set of experiments, imagine here you had like 1 million coin flips. Instead of n equals 5, you had 1 million. You would probably much more likely see that all of these like points, for instance, this one and this one and this one, would be much closer to 4 over 5. In words, this would say something like the sample mean the variation between the experiments is not that high. And we mathematically see that in the sense that the variance of the sample mean is the variance of the original coin, but it goes down as 1 over n. So as you increase n, the variance goes down. Okay. And I'm going to mention one more thing that you don't actually need to know for anything, but it'll hopefully help you with the intuition and something that you'll probably see again at some point in the future. So here's the story. So first of all, it says that as n increases, the variance of what? Not the original random variable. That's like some fixed variance. It's the variance of the sample mean. Okay, and maybe here I write this x bar, so you're not biased to the Bernoulli case. So the variance of the sample mean decreases. Okay, so this is beautiful, and like this is the way you'll see this stated in other places. So it turns out that the probability distribution of the sample mean, right? This is a different random variable than the original coin. This is like n coin flips. So what is that distribution? It turns out that it's approximately equal to the normal distribution. Okay? But what's the expectation of this normal distribution? Well, it's exactly the two things we just calculated. So it has expected value, the expected value of this sample mean estimate, and it has variance, the variance of the sample mean estimate. Okay, and we'll plot this in a second. But the thing you might have heard before is that this approximation is called the central limit theorem. Okay. And you're not going to need to know like the mathematical statement or anything for this. But this is the intuition I want you to take, is that it turns out that any one of these like sample mean estimates as you take n larger and larger and larger, its distribution gets closer and closer to a normal distribution. And the important thing is that, remember this parameter, this is the mean of the normal distribution, or the expected value, fine, as we would expect. And this is the variance, and this thing's constantly decreasing. Okay? And so visually, this is the kind of plot you would see for something like this. So remember, for the normal distribution, since it's a continuous random variable, we need to plot it, like we can only plot its PDF. And we'll discuss the PDF interpretation one more time in a second. But here's like what you might see. So, okay. So we're plotting densities. And here is the x-axis. And this is like the values. And maybe like alpha is over here. Okay. And so now let me plot what this PDF, right? I'm trying to plot, so this thing is a distribution. It has a PDF that you can use to calculate any possible probabilities. So we plot the PDFs. So let's plot the PDFs for different values of n. So here's the plot you might see for a small n. And this is supposed to be the bell curve. Okay. And so this is the PDF of what? Of alpha hat. And let's do it for, let's say this is 10, n equal 10. And so this is a PDF of the random variable alpha hat 10. Now suppose we increase the number of samples to, like, let's say 100. What you'll see is that the plot looks different. It looks something like this. And we'll interpret it in a second. And this would be like the PDF of alpha hat of, let's say, 100. And then finally, if you like did even more samples, what you're going to get is something that looks like this very peaked thing, and then like that. And this, say, is like the PDF for alpha hat 1000. Okay. What is the intuition I'm trying to get across here? The intuition is that this is the PDF, okay, of this random variable, the alpha hat, as n is changing. And what we see is that, okay, what you're supposed to see is that the peak of these things are all at the same point, but that's maybe not so apparent. But like all these peaks are supposed to be at the same point, which is their expected values. It turns out that's the expected value, lines up with the peak of this bell curve thing. But what you see is that, okay, so what we saw is that the variance should decrease. And the way we see this through the density is as follows. We see that the density has, okay, like what is the probability of something? It's the area under these density curves, right? So the probability for when n is much larger of this random variable, which is like the alpha hat with some n value, the probability that it's something much larger than alpha, which would be like over here, is very small. There's a very small area under the density farther away. And there's a very large probability that's in this area. Okay, so this is all I have to say about the coin flips. But the point of the story is that the sample mean is going to actually give us an estimate of the true mean of the thing we care about. And the second important point is that we increase the number of data points, which is going to be as we make the data set larger, like n larger in the data set in our case. What that means is that the variation between our, like the estimate and the true thing is not going to be so large. So we're going to be estimating almost the thing perfectly from just like even one fixed experiment, which is what I talked about before, one fixed data set of size n. Okay, so let's formulate this all in the machine learning world of estimating losses. And as I'm writing, is there any questions about this coin flip? Yeah, up there. Yeah, that's a nice straight line, right? Okay.
Like when we have a variance x plus variance x, like all the way, like all of those.
Yeah.
And then we're just multiplying variance x by 1. Wouldn't that be assuming that every single point is the same?
That's right. It is assuming that, but we know that's true because the variance is just the expected value of like the random variable minus its expectations squared and stuff. And it turns out that since the distributions of all the coins are the same, their variances are all the same. I didn't like formally show this, but this is true. Like you can like sort of believe this is true, right? Like the variance is just by definition the expected value of this function, which is like something squared. And what probability do you take this expectation with respect to? Well, you take it with respect to the like the true distribution, it's this. So they all have the same distribution, meaning all their variances are the same. Yeah, so if they're identically distributed, that immediately implies that the expected value and the variance is the same.
Same distribution, basically that means that, like, no matter what coin you flip, the probability of getting heads and tails is the same for all of those.
That's right. That's right. But when you actually do an experiment, it does not mean that you're going to get the exact same thing for each one. It just means the probability of getting heads or tails is the same. It doesn't mean that I'm going to get heads on the first flip and the 10th flipped as well. Cool. So now we get into like the actual thing we cared about. And here, things are almost the same story. So what do we have now? We have these feature label pairs, which before I called like Z. I'm just going to actually explicitly write them, but, and they, so here, okay, so here is some like feature label pair. I haven't talked about the data set or anything yet. This would be like equivalent to the X for the coin flip. We said this thing comes from some distribution P of XY. So this is like the feature label pair. I'm not going to write it for the sake of time. And then we have another thing, which is like, okay, the point is that these things, this is a multivariate random variable. Okay, I'll just write is a random variable. This is all I want to emphasize here. This is a random variable. We have this thing, which is a predictor. Right, it takes in just X. Since it's a function of a random variable, this is also a random variable. These are the things I want to emphasize with this. And then finally, we have this loss function, which takes in the predictor and takes in another random variable called Y, takes in two random variables. This is still a random variable. Okay. So before we had the coin flip thing, which was represented as X, which was a random variable, we wanted to know its expectation. Now we have a more complicated looking object, call this the loss function of X and Y, still a random variable. Guess what? We want to know, but we don't know we don't know. We don't know the expected loss, which we wrote like this. Okay, seems to match what we've seen before. In the previous case, all we had here was X, if you remember in the coin flip. Now we have a more complicated random variable. We don't know it. We just talked about how we estimate this thing. So we follow exactly the same steps. I'm not going to do all the like derivations and stuff because everything holds in the same way. But the story turns out that we can estimate this expected loss of our a predictor F with which we have like with n feature label pairs. Okay. So before we estimated with n coin flips, now we're going to estimate it with n feature label pairs. Okay. So before we introduce this random variable of n coin flips, now we introduce this random variable of n feature label pairs. What did we call it? We called it the data set. Okay. This thing looked like n feature label pairs. Oh, these are random variables. Great. And so had the same properties as the coin flip thing, which was that where each one of these comes from the same distribution. What was it? It was the original distribution we cared about. We cared about the expected loss of these things, which came from this distribution. This is the same distribution we have our data from. This is the standard assumption in machine learning, that the data comes from the same distribution as what you care about in the future of predicting. This is like maybe not so realistic all the time, but this is the assumption. Okay. And they're independent. Okay. So given that this is the exact same setup as before, with more complicated looking random variables, everything holds in the same way. And so now we define our estimate of L hat, or sorry, of L. And what is that estimate of L, the expected loss? We call it L hat. This is our estimate. It's an estimate of the loss, the expected loss for a predictor f. And how do we write it? Well, we write it as you would expect. You take the first random variable. What is our first random variable? The predictor at x, at x1, and the label at 1. And then you add it up with all the other random variables up to the nth one. Okay. So at the top, we've got our n random variables. Once again, they're these more complicated looking things than before, but they're still just n random variables. And we take the sample mean in the sense that we add them all up and divide them by n. Excellent. Since everything works out as before, it turns out, okay, like, that doesn't turn out, sorry, like, I'll write in a second, but like a simpler way to write this without this numerator thing at the top is you use this like summation notation again. You'll see this a lot. And you would write it like this. Okay, so just to familiarize you with this notation that you'll see a lot. Great. So now, using the same story as before, it turns out we can take the expected value, right, of this random variable, which is the sample mean of L, the expected loss. So the sample mean, or you would say it's like, we're going to estimate L using the sample mean. Okay, so anyways, we can take its expectation. And then the same way as before, you can show that it's exactly the thing that we were trying to estimate, which is L of F. It's literally the same like three steps as before. That's really good to see, right? This is the thing we want an estimate of. We can use our data set to get an estimate of it. Here's another thing, the variance, right? We can do the variance as before. What is the variance? Well, just like before, it's just 1 over n. So as n increases, the variance goes down. And it's multiplied by what? Multiplied the variance of the original random variable. What's the original random variable? That is L of f of x and y. Okay. Before we saw that this was just the variance of x in the coin flip example. Now it's the variance of the corresponding random variable, which is the loss. What does this tell us? This tells us that, like, for a predictor f, right? So far we had like and this is going to be important. We've had one, we fixed the predictor f. We said like we have some function f, and we take the function based on x, and then we apply the loss and whatever. But for a predictor f, the variance of this thing, okay, like, yeah, the variance, okay, I'll put in words. The variance of the expected loss for this predictor decreases as n increases. Okay, as we would expect, you increase the data set size, we have a better estimate of the expected loss of a predictor. Okay, and so we're almost done with this estimation stuff, but then there's one thing that is important to point out. So I'm going to point it out, but we're going to kind of skip over it for the next couple of weeks, which is that you might notice that, okay, so like before I do that is like, we're in a good place right now. We can estimate the loss, right? We can estimate the expected loss for a predictor. Seems the estimate's pretty good. It gives you the true thing most of the time, in the sense like that its expected value is what we want, and its variance will go down as we increase the data set size. Seems pretty reasonable. Then our approach before also seems reasonable because now we have an estimate of this thing. So all we need to do is search over all the different f's and pick the best one with respect to L hat. Okay. But do we really? Okay. And so this is actually a pretty nuanced point. So what you should remember is like we need an estimate of L of f, not just for one predictor f, right? We need it for all predictors. So we need it for all f in the function class f. Okay. And at this point, I don't expect you to see why this is of any problem at all. But just keep in mind that in the coin flip example, what you said is you had some random variable, it had some expected value. And then what you would say, like in usual probability world, is you then like do an experiment or you gather data, and then you use the data to estimate the random variable. or sorry, to estimate the thing you cared about, which was like the true mean of the coin flip. Here, this also works if we have like a fixed predictor, which is like you have a predictor and you gather some data, and then you take the predictor on that data, you take the loss, and then you estimate it for that predictor. But now we're saying, okay, I want this data to be useful for estimating not just the loss of one predictor, but of like a lot of predictors. There's actually infinitely many, and I want it to be good for all those somehow. And then, based on that data, and here you might see something that's a little bit funky, which we'll talk a lot more about in the next class, like in a few weeks, not for now, which is that based on the data, I'm now going to pick the predictor that kind of best fits the data. This should kind of be a red flag in your like probability world, which is like you do an experiment, you gather data, and now you look at the data and you're like, oh, on this data, this is the best predictor. Like I can just like pick the one that fits perfectly through all the points and so on. And this is just like the high level intuition. This turns out to be a bit of a delicate point of when you can do this. Like when can you basically, like usually in probability where you design your experiment, then you gather data and you evaluate it. Here we're saying like, let's gather data and then pick the best thing based on the data. This turns out to be a bit of a dangerous endeavor. But let me write some things about it and then, yeah. So the question is it okay to use L hat of F based on the same data set, D, to estimate the thing we care about, which is the expected loss. And the important thing is that, is this okay if we do it for all? Okay. And I give you the answer, which is an unsettling one for now, which is it depends. Okay. And yeah, so it depends. And what does it depend on? It depends on the size, on how large n is, yeah, and how large f is. Okay. But we will discuss this later. So this is going to be coming up in like maybe 3 weeks about when we talk about evaluating our predictors. And there you hear these like famous terms in machine learning called the bias and the variance, and the bias variance trade-off. And it's all about this. And you're going to trade off these two things, which is like, yeah, like it's going to depend on how large n is in this. And then the short story is like, if you make n really, really large, then it turns out to be okay. And if you make this thing really, really small, it's also okay, like the function class. But if you have a really big set of functions you want to pick from, and you have a very, very small data set, there's some problems. And that should kind of intuitively also make sense. Like if you just had like 1 or 2 house prices, and you pick like such a complicated function that like has all this like curvature and fits it well, it's like, okay, do you really think that's a good predictor for it? Probably not. Okay, so that's the answer. And so so what do we do? So for now, we use L hat of F for all F and see what happens. And yeah, so we're going to use this. We're going to find the best F based on this thing and see what happens. And you'll code this up in not the next assignment, but the one after the midterm. And you will see what the story becomes. Okay. Yeah, let's stop there for the estimation thing. I will actually use 5 more minutes. Okay, I'll answer this question. I'll use the next 5 minutes just to briefly start you on the story of optimization to get you interested. The question online was, will there be a midterm practice? And the question is, so there's gonna be a midterm review session on Thursday. Regarding the midterm stuff, I'll share info definitely by the next class on Tuesday. Like I'll post info and like a formula sheet and what's gonna be on it and stuff, and like some high level thing. On Thursday, I'll definitely go over the details for this. The really short story is that like, it's gonna be like the same story as the assignments and stuff. Like if you can do the assignments, you can do the midterm, You're not going to see like any big surprises and stuff. Yeah, we'll talk more about it on Thursday. Okay. So anyways, what have we done so far? What we've done so far is that we've basically like checked, if we go to the supervised learning business, what we've done is we kind of like, okay, I'm going to erase this there, but we've checked this guy off. Like we have an estimate, we've done the estimation part. What's left is to study the optimization part. And so we do a very short 4-minute story to warm you up about this. And hopefully we can finish the very simple version next Tuesday, because that'd be beautiful. Okay, so how are we going to search through all these functions? And I just wanted to, so this is optimization. And the story, like, what is optimization? It really is this story of like finding the best solution from a set of possible solutions. Okay. Already seems to fit our needs. We have the set of possible functions. We need to find the best possible function. Okay. And the way you've seen this before is that usually this means finding the minimum or maximum value of some function. Okay, this is basically what you're going to see is we're going to try to minimize or maximize functions. We need to minimize the loss, well, the estimate of the loss. Great, so we seem to be also in line with our needs. And in particular, we're going to care about things like this. We will So we'll care about things, and we will write it like this. We'll care about having a function g of w. And I'm going to use w because we're going to use w later on for machine learning stuff, and w will be like this parameter thing. But it's the same thing as a variable. We call variables parameters, variables, whatever. And you're going to have this function, and your goal is going to be to minimize the function. So we write minimize the function over all values of w from some set calligraphic w. And this is to be read as this thing gives you the minimum value of the function g of w over all little w from the big set w. Okay. So write this, and I just write one more last notation, and then we'll end it there. So we'll care about finding either the minimum value of this function or the argument, so the value of w that gives you the minimum. So we write the argmin, and this is notation that you should get very familiar with, which is we'll write the argmin, which gives you the, so we'll write the argmin of GW, and what does this mean? This means this gives you the little w from the set, and gives you the value of the little w that achieves the minimum value of g of w. Okay, this min thing gives you the value of g of w, argmin gives you the value of w. And in particular, what that would mean is that this min of w, or g of w, this gives you the value of it. Well, this should be the same as g evaluated at, okay, I should give this thing a name. We're going to usually give this thing a name of w star. The thing that achieves the min is going to be like this special w star. So at g w star, you achieve the min. Okay. That's all I wanted to say. This will be a very important thing to note, and our story is going to be to search through this set. Okay. We will end it there.